this is a problem on radioactive decay, and the equation for it, let me highlight the equation for you. The equation is given right here, so you don't even have to go look that up. A0, A is the amount that you have at some time t. A0 is the amount you start with, and it's multiplying 2 raised to the minus t over h. H is the half-life. I used h for half-life just because it's easy to see. Usually people use ta or t with the subscript of 1/2. Right. First thing to remember in these problems is that you don't multiply the A0 times the 2. PEMDAS holds, and you work this out as though it's in parentheses. Then you multiply by A0, which is the amount you start with. In this case, you're going to start with 200 grams, so A0 will be 200. The next thing, and that's why I'm having you do the problem like this, is that you have half-lives that are some strange numbers, like 458 years for americium-241, which is probably in your smoke detector. Okay, so that's in 458 years for that material, for half of that material to be gone. Another 458 years for half of what's left to be gone. So this is your half-life business. If you work with the 458 years, you just get unwieldy numbers. But you can work in terms of half-lives. One half-life is 458 years. So if I count by 458 years, then I will see the pattern without even having a calculator. So I'm starting with 200 times 2, and in 400 in one half-life it's 458 years. Okay, so I have minus, whoa, I ran out of, no I didn't, 458 divided by 458. You see, that means I've got 200 times 2 to the minus 1. Right. So 2 to the minus 1 is the same as 1 over 2, which is half. So I've got 100. One half-life later, I have 100. 2 half-lives later, I'll do that calculation, and then you can see. Maybe I'll leave a little more room. I'll take off part of this. There we go. Okay, so let's look at 2 half-lives later. What you can do is put the value for the half-life in. 2 half-lives later would be 2 times 458. Oh, I see, I left myself exactly the same amount of room because I wrote bigger. Those cancel, and I get 200 times 2 to the minus 2. Okay, 2 to the minus 2, it means 1 over 2 squared, which is 4. So 400 divided by 4 is 50. So I started with 200. In one half-life, I'm down to 100. In another half-life, I'm down to 50. How about 3 half-lives? I'm down to 25. When you count by half-lives, you can see the pattern automatically. Just because one half-life equals, in this case, 458 years, who cares? You can restore that later if you want, but generally people talk in how many half-lives out. So if you're 5 half-lives away, you're generally pretty close to, well, most of the action's over. You know, your graph looks like this. You start at 200. In one half-life, you're down to 100. 2 half-lives, you're down to 50. 3 half-lives, 25. You see, after a while, most of the action's over, and you're coasting in towards 0, although you never get there. Okay? So I want you to get used to this idea of a half-life. Another way that this is called is a time constant. You're counting by time constants. In other words, you're using whatever time it takes so that the exponent for the 2 is going to be 1, 2, 3, 4, 5, 6, 7, whatever it is. Alright? And when you count by half-lives, you see the pattern. Now for this part of the homework, you are given linear paper. Linear paper is the usual paper that you've always used, where you have a linear scale in X and a linear scale in Y. And then you're also given a appropriate piece of semi-log paper. And in semi-log paper, the the time axis is linear, but the y-axis has a logarithmic scale to it. And you take those numbers and you plot it into the log paper. So I'm not going to go over that in this homework. There's another lecture on semi-log paper, and also there'll be lectures in class on semi-log paper. So basically you use the paper that's provided in the homework to graph the results. If you remember what happens, here's what happens. In your linear paper, you have a curve that looks like this. Okay. So here's my time, and here's the amount of radioactive material. It'll start at 200, and it will go down in a pattern like that. This is linear paper. On the logarithmic paper, time is here, and you have the different logarithmic scales, right? Big jump, and then it kind of scrunches in. Big jump, and it scrunches in. You just plot the numbers, find the number here, and correspond it to the time. You can use half-lives, so you don't have to use the 458. And that graph, instead of being a curve like that, will be a straight line. And this is on your semi-log paper. Here's the similar problem for growth. So here's equation for radioactive decay. And it's T over some constant, I'll call it tau. Okay, here is the one for growth. Okay, they're identical except for a negative sign here for decay and the plus sign here for the growth equation. So here we're talking about the growth of bacteria. It's E. coli bacteria, and it occurs every 20 minutes. It's going to double itself. So you're going to start with 100. So your A naught is going to be 100. So I've got A equals 100 times 2 to the T over 20. So now you put these values in, calculate it on a calculator or figure out the time constant, and you can work through that. Starting here with 100. In 20 minutes, you've got 200. Okay. I skipped 40 here. In 40 minutes, you would have had 400. And then there's log paper that's given. Again, if you had to graph this, let me just give you an idea here of what's going on. If you graph this on linear paper, you would start with 100. And before you know it, there's time. It goes like this, and then it just starts going up like that. This is linear paper. You get a curve like that. On your semi-log paper, here's the amount with its logarithmic scale here. Big jump, and then it kind of more lines up here, more lines up here. And here's your linear scale. You again start with your 100. But the result is going to be a straight line. This is Moore's law, and I'm going to work it out entirely, and I'm going to do it two ways. It's interesting. Okay, Gerald E. Moore was one of the co-founders of Intel, and he observed back in the 50s that it seemed that every 18 months technology doubled. The amount of transistors you could get for a certain amount of money doubled. This law has been applied to the number of pixels on a screen, many things in technology. It seems like 18 to 24 months seems to be the doubling time. It's also been pointed out that people price things according to this law, so that it's sort of been a self-fulfilling prophecy here. But let's go ahead and see how it works. So the data that we have is that in 1956, one transistor cost $6. Okay. Then we're going to go up to 1997, and at that case you could get this DRAM that had 16 million transistors on it, so that's 16 times 10 to the 6th. That's how many transistors you got, also for $6. Remember, 10 to the 6th is a million. And now you want to see if the law holds, and the law said 18 months for this doubling time. So what we're talking about is time in months. So let's figure out how many months there are between 1956 and 1997. Turns out that's 41 years, which is the same as 492 months. Okay, using that, I'm going to show you two ways to solve this problem. Okay, here's one way to, we're trying to verify that law. So here's the basic equation. A equals A naught times 2 at the times 2 to the t over the doubling time. I know that the amount of transistors was 1 when we initially looked at this problem at 56, and now it's 16 times 10 to the 6 is what you have. So we can solve either for t or d. Let's say we assume that the doubling time is 18 months, and let's see how many months it would take under that rule. So I've got the 18 over here. Okay, the one is now, of course, invisible essentially. So now I've got to get the t down from being an exponent. So I'll take the log of both sides. I've got the log of 16 times 10 to the 6th equals the log of 2 raised to the t over 18. The t over 18 is going to come out in front. And I have to evaluate some numbers. Log of 16 times 10 to the 6, you can do that on your calculator. It's 7.2 something, 7.204 I guess. And now I have t divided by 18 and the log of times the log of 2, but I know what the log of 2 is. That's t over 18 times 0.3010, good enough, 7.204. And now if I've got 18 times 7.204 divided by 0.3010, and that's the time it should have taken under the rule, and that turns out to be 430.8 months. Okay, the prediction was 492. I would say that's pretty good. Now let's do the problem a different way. I'm just going to leave a lot of it the same. Actually, let's get rid of this and this. And now I'm going to say I know how long it took. Let me see if I can figure out the doubling time. Before, the prediction was, I'll get the pen, D was predicted to be 18 months. Let's see what we come up with these numbers. 16 times 10 to the 6th goes here. The 1, which I'm not going to bother writing. And now I know it's 492 months over D, and I want to solve for D. Okay, so I take the log of both sides. Log of 16 times 10 to the 6th equals the log of 2 raised to 492 over D. Okay, this term is going to come out in front. So I have the log of 16 times 10 to the 6th, know that already, 7.204, and that equals 492 divided by D times the log of 2, which is 0.3010. Now I can solve by D. I put D on this side, and of course I have to divide. 492, 7.204, 0.3010, and the predicted answer, the calculated answer is 20.55, which is very close to 18. Plus, I think Moore said 18 months. A lot of people say it's 2 years, so that's right in between. All right, that's how to do that problem.